Look up at the night sky today and see points of light across a dark void. But if we rewind 13.8 billion years, the universe wasn't dark at all. It was a blinding, completely impenetrable white fog. In the fractions of a second immediately following the Big Bang and a period of rapid expansion known as cosmic inflation, all the matter and energy in the universe was squeezed into an unimaginably tight space. The ambient temperature was soaring at billions of degrees. This extreme heat created a photon-baryon plasma. Atoms were stripped apart into a superheated, chaotic soup of free electrons, protons, and photons violently smashing together. Light simply couldn't travel. A photon couldn't move a millimeter before ricocheting off an electron, trapping it in place. With light entirely trapped and matter distributed almost perfectly evenly across the expanse, there was no empty space. That meant no gravity wells, no formed planets, and absolutely no stars or galaxies. The early universe was a glowing wall of energy. The cosmos we know today couldn't begin to take shape until this primordial fog finally found a way to clear. It took 380,000 years of constant cosmic expansion for the universe to stretch out and cool down to a temperature of about 3,000 Kelvin. This drop in temperature triggered a massive phase transition called recombination. Recombination is the exact period when the universe cooled just enough for negatively charged electrons to slow down and get captured by positively charged protons, binding together to form the very first neutral hydrogen atoms. By locking those free electrons into atomic orbits, vast amounts of empty space suddenly opened up. The photons that had been bouncing off particles for hundreds of thousands of years shot forward in straight lines, completely unimpeded. That initial burst of freed light is still traveling through space right now. We detect it today as the cosmic microwave background, a faint glow of radiation that serves as the oldest visible light in the universe. But achieving transparency came with a catch. The moment the fog cleared and that initial light moved on, the ambient glow faded to black. The cosmos entered the Dark Ages, an era composed entirely of gas, with absolutely no stars to light the way. For millions of years, the universe was little more than vast, drifting clouds of cold, neutral hydrogen gas, expanding outward into the void. Left to its own devices, this expanding gas would just keep spreading out. Without a strong enough localized gravitational pull to organize it, the hydrogen would never compress tightly enough to ignite a star. This image shows a simulation of the vast web-like architecture of dark matter filaments. Dark matter is an invisible form of matter that doesn't interact with light, but exerts a massive gravitational pull. Tiny quantum fluctuations from the very first fractions of a second of the universe had seeded these massive invisible structures. These dark matter halos acted like massive gravitational nets. They caught the drifting neutral hydrogen gas, dragged it down into their deep gravitational wells, and forced it to pool into incredibly dense pockets. While the universe appeared completely empty to the naked eye, this invisible scaffolding was actively organizing the cosmos, building the precise conditions needed to end the dark. Deep inside those dark matter wells, the pooled hydrogen gas was being squeezed under immense pressure, driving the internal temperatures higher and higher. Eventually, the core temperature crossed a critical threshold, and nuclear fusion ignited. This birthed the first generation of stars, massive, brilliant, and short-lived. These new stars pumped out intense ultraviolet radiation, kicking off the epoch of reionization. This light shredded neutral hydrogen atoms, stripping their electrons into a plasma. But because cosmic expansion had stretched space, these freed electrons were now too far apart to block photons. Starlight could now travel freely through the newly reionized gas. The universe was finally both transparent and illuminated. We don't have to rely purely on mathematical models to know this sequence is real. Because light takes time to travel, looking deep into space means looking directly back into history. Instruments like the James Webb Space Telescope are built with highly sensitive infrared sensors. These sensors detect longer wavelengths of electromagnetic radiation, allowing astronomers to see ancient starlight that has been stretched out over 13.3 billion years of cosmic expansion.
Using these sensors, astronomers recently observed 3 of the earliest known galaxies right at the cosmic dawn. They caught them in the exact act of pulling in that cold, neutral hydrogen gas to fuel the first major bursts of star formation. Every star shining in our night sky is the result of that long, mechanical process. The cosmos had to expand out of a blinding fog, drift through millions of years of total darkness, and rely on the invisible pull of dark matter before it could finally switch on the light.